Welcome to You've Lost That Process Feeling, Lessons from Resilience Engineering for SREs.
I'm Dave Woods. I've been involved in understanding how people cope with complexity in complex dynamic worlds for decade upon decade. And in that process, I come across the criticality of process feel in many, many different settings. Even when I'm not looking for it, it turns out to be an important aspect of how people can understand anomalies and how to intervene to restore systems to functionality when things go astray. I've even tried to design computerized systems to support people in this form of cognitive work.
I'm Nolan. I have been in this industry for some time. I spent a bunch of years at SRE at Google, and I'm currently at Slack. I'm a contributor to various things such as USENIX Login magazine, the SRE book, and like 7 things that every SRE should know. I'm here to kind of bridge the gap a little bit between theory and practice. In other words, Dr. Woods is the expert here, and I am here to stop him from using too many big words.
Well, let's start out with what really process feel is all about. And so this little vignette occurred when we were studying how people made decisions in emergencies. Team of operators, dynamic, highly complex, highly interconnected process. And we were watching a variety of simulated emergencies, nothing really going wrong with nuclear power plants, and watching how operators understood what was going on and fixed things. And we kept observing that the operators knew to go over to one section of this giant control board, not really computerized in those days, and check out this one major control system. It was automatic control, and it controlled how the reactor itself worked. Rods went in and out. And the position of the rods was indicated by mechanical counters, which clicked. So we were trying to figure out why all of a sudden there was no explicit signal, no message, no alert, no alarm that led the operators to go over and check out this automatic system of this critical function. Finally, after observing them in the several different simulated emergencies, we finally realized what was going on. And we said, well, what's happening is when they don't expect, right, the automatic control system to doing anything, and they hear clicking and it's doing something, they go over and check. And when they expect the automatic system to be doing stuff, but it's quiet, they go over and check. In other words, they checked when their expectations were violated. So we went to them and said, what's going on? And previously, they had never been able to tell us how they were, understanding where and how to monitor different aspects of this complex process. And they said, well, but of course, right? They couldn't tell us directly. It was an implicit kind of skill, but when we brought it out, it was clear cut. This was an explicit, important source of information about where to look, what was anomalous, and how to follow it up.
How does this relate to us? I mean, I don't run a nuclear power station. I just run some web services. I have all this great stuff. My systems are fault tolerant. I have testing. I have canarying. I have progressive deploys and rollbacks. So I'm good, right? Well, the problem is, no, we don't run nuclear power stations. I'm glad, and I don't want to be on call for one of those. But what I think has become evident in the last few years is that the impact from software services going down can be quite significant. There are sometimes safety implications. I mean, thinking about reports of self-driving cars that stopped at the side of the road because there was an authentication service outage, and so on. But most often the implications are just disruption on a large scale. But there are very, very real challenges in operating software services, and you're all at an SRE conference, so you probably know this. But it's not getting easier necessarily, right? The last decade is the story of just increasing automation in how we control our systems. We've got auto-scaling, dynamic load balancing. 10 years ago, 15 years ago, we were administering systems, and now what we do is we build automation that administers our systems. So we need it. It saves us a lot of time, it saves us a lot of effort, but they are another layer of indirection that makes it more work to understand what's going on in our systems. Add to that, software is less observable than physical systems. We can't see or hear anything directly. We don't have clicks. Our dashboards can lead us astray in quite interesting ways if we're not careful. Our systems, they change much, much faster than aircraft or nuclear power stations do. So we're always dealing with this, huge rate of change. So dealing with problems in software systems, it's hard work.
Well, speaking of change and highly automated systems, things that we would today call very autonomous, we can think about something that was planned for space station that we had a chance to work on to help out a little bit with. And it illustrates the importance of process feel, especially in these highly automated worlds where change is going on. So on a space station, the thing you have to manage is energy, right? You don't want to be too hot, and you don't want to be too cold, and those can vary pretty extensively. So they were building an energy management system that is highly autonomous in today's terminology. We can do that with classic engineering techniques, some very inventive kinds of mechanical and thermal engineering to move energy around. We don't want to overload any part. We don't want to underload any part. So there's underload here, not just overload, right? Though you take advantage of that sometimes to move resources around. And the key was it was very dynamic, right? These condensers and evaporators and special kinds of valves and things that were, in a sense, kind of agents, even though mechanical agents. So the question was, we wanted to design in that day AI. Why? Because every good system had AI, sort of like today, and we were going to have AI as a diagnostic system to figure out when things were wrong. And then there was going to be a human-computer interface for the astronauts and ground flight controllers to know what was going on when the AI tried to figure out what went wrong, right, and how the system was working or not working as it should. Now, the problem was it was highly automatic and dynamic. And it was under construction and analysis, so the design of the thermal system kept changing. And every time they changed the system, they had to change the way they were doing the AI diagnostic system, which meant they had to change the human-computer interface. It was sequential, it was slow, it was expensive. Things were not going well. We were asked in, as part of our projects with NASA, to take a look. And what we quickly realized was that if you step back and thought about what are the different functions, the jobs, the different physical components and subsystems are carrying out, and seeing them as automatic and dynamic, we could lay out the basics of the way it was supposed to work under a variety of situations. And that was the key. There was no ability to have a good process feel. Are we where we're supposed to be? Are we doing the things that are supposed to happen given this energy context? Where are the loads? Where do we need to move it? What do we need to get rid of? Where do we need to keep it? All of that was super contextualized. So how do I know where I'm supposed to be? So that was the key ingredient we used, was to design displays that allowed you to see dynamically, this is where we think we should be. This is where it looks typical for this context. And once we had that, actually we didn't need as much AI, because the people could see what was going on and could track it when anomalies occurred. And the diagnostic process improved directly.
What I really want to know is, did the space station get built?
Actually, no. The picture we showed was the design intent by an artist, because you don't see that actual configuration of planets. And instead, we went to go with the International Space Station, sharing it with others.
What did you find? We found that each of these difficulties exists in software systems as well, sometimes even more so. So the complexities of our systems may not be well understood. If we're not careful, we can end up with a lot of metrics and alerts that are not necessarily helpful. And anomalies and incidents often spread or shift to different parts of our systems, so we can get cognitive overload, pager storms, and just general confusion.
So what we've been describing so far is an idea you may have heard from John Ospal. Richard Cook laid this out: above the line, below the line. And the line is a line of representation. What is it we create so that we can see into the software system? Just like we were trying to create representations to see into the thermal management, energy management system. Or we created representations to see how the automatic control systems in the power plant were working. All of these things were hard to see, and it takes work to design representations to reveal what's going on in a dynamic, changing world with anomalies occurring. So what were we studying, and what's process feel about? It's one of many kinds of properties about the cognitive work above the line, the joint activity of various parties as they try to do the cognitive work in anomaly recognition and diagnosis and intervention. And of course, we've studied quite a bit about these different functions in cognitive work, the stuff that goes on above the line, monitoring, reframing, replanning, etc. Now, below the line, we've heard Laura talk about some of the kinds of capabilities that you build in trying to make systems fault tolerant, respond effectively to different kinds of problems that arise. Again, a dynamic, active, right, highly autonomous system that works at scale. And because it works so well, it keeps growing and changing, right, creating even more complexities to make sure that the people above the line have to be able to handle some of the time.
We're working above the line all the time. It's everything that's not in Jira. It's all your day-to-day work of investigating minor weird things, making sure the feature you just launched is working properly and hasn't had any adverse effects on performance. Even deciding how to best implement something. We're constantly doing this work, and there's no sign that human role is getting less over time. Despite 20 years ago being told that fourth generation programming languages were going to put us all out of business, it's just not happening.
So we've explained one factor, one kind of path about monitoring a complex dynamic system, process feel. How do I know where the system is now, where it's supposed to be, as expected, as planned for, giving a dynamic, automated world with lots of different contexts? But there's two other paths we want to talk about as well, because right, the other one is pretty obvious to all of us. It's about alerts, and we want ones that contain a lot of information. And they tell us about when our system isn't where it's supposed to be. And where is it when it's not supposed to be there? And how do I get it back to where I want it to be? And so the shift from is it where we expect it to be to right, it isn't where we want it to be are the two classic ones that people use to represent systems. We've been highlighting that process feel often gets short shrift when it's actually a pretty essential aspect of expertise, even though, as in that first example, it can be quite implicit, right? Hard for people to talk about, yet it's very central to the kind of expertise they have in incident handling. But there's a third path too, and that emerges from the recent work in resilience, particularly the discovery of this idea of graceful extensibility. And that gives us to another path, and a path we'll talk about, because it's about how is the system getting overloaded. So think of this path as approaching overload. And what's the behavior of different functions and subsystems when they start approaching overload? And how does that affect other parts of the infrastructure when one part or function is experiencing overload or getting there? What does it do, and how does it spread, or how does it get contained? Now, when we talk about alarms, all right, that's that second path. Remember that the classic way that was often formulated is called the dark board. In other words, you don't tell them anything until something goes wrong. Everything's fine until it isn't. And of course, that can be rather jarring when you're trying to monitor a system and everything's quiet, everything seems fine, and all of a sudden, boom, right? You have to reorient and rethink and start investigating things. And to some degree, that kind of dramatic shift, something we've studied in cockpits, for example, when incidents happen there, isn't really the way you want to go. You don't want that shocking transition. So you actually want to give people process feel. So a dark board by itself isn't sufficient, and that's where this process feel stuff comes from, and should be supported in the way you develop your systems for incident response. Now, this also is a problem because in the cases we were looking at, just like your system, the complexity means a lot of interdependencies. And interdependencies mean that, remember, there's difficulty in observing what's going on below the line means that effects at a distance happen. Effects at a distance mean they're far away from what's driving things to start the problem, or the trigger that started the problem. And so multiple effects spreading through the system make it hard to understand where to intervene, what's the critical thing to act on. You've all been there. And of course, the third thing is alert overload. And we've all been, whatever setting we work in, all the settings I work in, people get lost very quickly in an overload of alerts.
I think this should make intuitive sense to us. Most of us have been there. And even if we haven't been on the wrong side of a pager storm, I think that we see that The wrong kind of alert setup can lead to a lot of day-to-day sort of noise and waste quite a lot of time investigating things that turn out to be harmless changes in user behavior, for example. But I think this is best illustrated with a story. So this is not an outage story. This is really a story of how things go right. And it's thanks to process field and to kind of high signal alerts that helps the on-callers to focus on critical information. So in this system, we see that we have a load balancer tier, we have some web servers, and we have a control plane. The control plane's job is to health check the web servers and to tell the load balancer tier what the list of healthy web servers is. When an alert fires, the hosts in the load balancer tier have got less than half of these web servers in their endpoint list reporting healthy. So what happens here is you get a thing called a panic mode where they fail open. So they disregard health checks and just spread load across all the endpoints that they know about. This is something that we don't expect. This is sort of an emergency mechanism to prevent cascading failures. So this is something that is, we pay a lot of attention whenever this alert fires. So on inspection, it turns out it's only a tiny subset of hosts that are impacted. To take them out of service and investigate further. System is within SLO, so this is an anomaly, not an outage. But I think this is a great example of how SLOs alone don't tell us about our system state. We have a lot of ways that we try to make our systems robust and gracefully extensible, but to work in spite of a partial failure. And those mechanisms can kind of conceal impending problems until everything falls over, unless you pay attention to them like we do here. So is the system okay now that these bad hosts are gone? We don't know, because we haven't done the above the line work of figuring out what the problem was. But quite soon after this happens, some more hosts start going into that same failing open mode, and we get more alerts. And we also see some signs of saturation in the control plane. So the problem seems to be moving around. Scale up the control plane, and the problem seems to go away. So, okay, wasn't the control plane overloaded the whole time? We don't know. We just applied a generic mitigation, and we still haven't really fully investigated here. We had a sense that something was off because it just didn't seem right that the load would increase out of nowhere and cause this problem. So again, the system still in SLO, just maybe not where it's supposed to be. All faults.
Yeah, it's particularly nice what you just covered too, because that suspicion that you didn't really solve everything, you didn't really understand, and something might be lurking there that might come back, right? That is related to process field, right? And without having that process field to begin with, you can't have that kind of suspicious attitude towards what's going on and in understanding how an anomaly is handled in these situations. So the third factor path that has emerged recently is this idea that to handle overload, that all systems have limit. Any function, subsystem, any capability, doesn't matter, human, biological, computer, anything, it has limits. It has a range of capacity, right? And it can handle things within that range, but there's a boundary and the world will throw challenges at you. So you need to be able to extend performance, right? Very directly related to software extensibility. You need to do that gracefully from where you are in the middle of operational situations, transitioning, not that dartboard, boom, all of a sudden now we're into something's terribly wrong. What do we do? Where is it? How do we handle it? And so the key in this is the limits, that you will start to approach your limits. You will start to get overloaded. You will reach saturation. How you approach saturation, how you recognize that, how you behave near saturation as a unit in these networks and systems turns out to be very important, right? There's a triggering unit, right? A triggering event, right? And that changes, right, the loads on systems. On subsystems. And so a unit can start to approach saturation. How does it behave as it approaches saturation? And how does it signal other units that it interrelates with? And how do they behave as a interdependent unit starts to approach saturation? Right? Are you signaling clearly? Right? Or are you hiding things? Are you shifting load to others? Are you dumping it on other parts of the system so that overload starts to move around and other units approaching overload start to behave? Are there compensatory mechanisms that come into play? Again, often automatic ones come into play initially, trying to mitigate overload or to contain overload. All of this starts to play out as a dynamic, active process, making it even harder to figure out what's driving, what are consequential events, where do you intervene, what's really going on. And so this third path is if you can see how systems approach overload and behave near overload and how that interacts with other parts, you can tremendously improve how you design for process feel, how you can use that in incident handling, and how you can design better alerts and alarms so that you can hone in on what's really critical to intervene quickly and resolve the situation. Our problem with today's system is they tend to respond late as they approach overload. It gets pretty bad. That means they have to respond in a fairly big way. That's also not good, as opposed to gradual processes that can change direction as more feedback is gathered. And it often can dump load elsewhere, leading to spreading overload, spreading saturation. And then the automatic mechanisms for provisioning or deprovisioning resources to try to cope with this stuff often has a low sensitivity to what's actually going on. So it could kind of get in the way, and perhaps it'll deprovision some a resource thinking it's saving and helping when it's in fact actually taking out a mechanism that you need in order to monitor and diagnose the developing trouble.
And of course, this is one of the core challenges that we face in our profession. I mean, you know, putting together all the components so that our things work well when they're near the limits. And this is something that, you know, it really takes time to get right, and it takes testing. So this is why disaster testing and chaos testing on a large scale is so useful. We do know we have a bunch of approaches that help, that are similar to what we're talking about here in terms of graceful extensibility. So circuit breaking, limiting retries, throttling, sort of centralized quota management, load shedding, load aware load balancing, graceful degradation. So we can have multiple lines of defense here. So a system can do less work when it's overloaded. You can use stale results and things like that. And of course, you know, I'll say again, it's so important to monitor so that you know when you're using these mechanisms that are intended to help you cope in these bad situations.
So these mechanisms help a lot, right? It allows your systems to work more reliably and robustly. And therefore you can grow and scale up. On the other hand, when things do start to overload and saturation moves around, it becomes really challenging to figure out what's going on. Where is it going and how to intervene? You experience this in incident response all the time. So we have an irony here. You actually have already designed systems that have some attempt to handle saturation. In other words, you're already stumbling into what graceful extensibility tells you to do. You already figured it out in part, right? But as we commented before, these things are not done in a way that make the signaling and cross-signaling and the behaviors a little more coherent from a total system point of view, so that we're not pushing overload all around in some of the difficult scenarios. So you're the perfect opportunity to start to implement some of these ideas in a way that can take add to the reliability and robustness you've already built in and create much more of a high resilient performance from your system by taking some of these ideas, right? The critical thing is everything has a limit on their adaptive capacity. So you need a way to respond as you start to run out of adaptive capacity to handle continuing load and challenges, traffic. Your system is highly interdependent, so you need to have behaviors as you approach saturation, that mitigate it and don't spread it around and overload, produce a cascade of continuing overload. And you have to do this in a sense where every unit has only a partial view of what's going on around it. So you need to have ways to have an emergent picture and a shared picture that builds in, and that's critical to the incident responders, so that they can quickly hone in on what's going on, see it unfold, see that saturation grow, cascade across lines of interdependency, and intervene intelligently and quickly.
We have almost saturated our time. I'm going to quickly finish this story. So, where were we? We had not yet finished our above the line activity of figuring out what the heck had gone on. But we figured it out. We looked at some logs on some of the hosts that we knew were affected. And it turned out that the trigger for this event wasn't overloaded the control plane. That was an effect. The set of web servers had gotten bigger, and it had exceeded the max RPC payload size between the load balancers and the control plane. And then retries from the load balancers, even though they were limited and had back off, they still overloaded the control plane. And that was where that saturation came from. So this is what the timeline looked like. So above the line is kind of what we knew and understood, and below the line was what was really sort of driving the changes. So very quickly, we're going to wrap up what we've talked about here. But first, it's interesting to see how emergent systems can sometimes fix themselves. You'll often see this. You'll see a sort of system tipping over into failure or into overload briefly and then coming back. So I think one of the key drivers of reliability is understanding that sometimes you're seeing these signs that something is not right under the hood, and knowing that that process field tells you when to go and dig deeper.
So we have a couple quick takeaways for you. One is process feel is real. It's essential. It's a foundation for expertise in incident handling.
And you can do this in a bunch of different ways. Spread the work of investigating problems in different kinds of your system, different parts of your system around. Run practical training, not just theoretical design document reading training. Run practical tests in your systems. I'm a big believer in production meetings where we tell stories about, the anomalies that have happened in our systems this week and how we understood what was going on. You can also consider running surveys where you ask questions that are geared towards understanding if people feel that they have process feel in different parts of their systems. So, where are they confident, where are they not?
So alerts, as we've kind of indicated, tend to be a lot of them because they're low level. And so many of them tend to appear when something goes wrong. There's malfunctions moving through the system. They give you a fragmented picture. Now we have to put all those low-level indicators together. That's a lot of cognitive work above the line. Right? That's what we have to go through and struggle. And the key here is to move beyond threshold crossing. We have to think about relationships and constraints. And the other key is to step up and start to think about units in terms of the functions they carry out, like we were doing in the space station thermal management case. And that means we start assigning alerts and saying, this is what's going on as we approach saturation. As you start to use that idea, you can redesign alerts that are going to be much more informative and much more directive to where key problems are happening and how those are acting as drivers, spreading effects throughout your system.
Yeah. Instead of thinking about thresholds, think about times when your system is breaking some invariant. My control loop isn't finishing in time. Things are stale, things are saturated. It's system dependent, but it's important to think this way, I think.
So a lot of it comes from showing relationships. So it's differences over time, a difference in one thing, how it changes relative to another difference. We move away from simple threshold crossings. And we've done this in many situations. It's what the computer, right, enables us for building new, more sophisticated forms of representation. And our last one is you can apply the theory of graceful extensibility. It's not simply some esoteric background fundamental. It really is a practical guide. Right? It tells us about how systems will be brittle. They're brittle in the face of how they deal with saturation, right? And we can design systems that are much more effective at dealing with saturation by acting early and in small steps, by being sensitive to the approach to saturation. And if they signal effectively what's going on to people, as well as in terms of how they interact with their interdependent processes around them, your system can work much more effectively, much more resiliently, and the brittleness problem can be significantly reduced.
Thank you. We're out of time. There's a slide here with references that will be available. And thank you very much.
Thank you all.